Most people use linear regression without really understanding it. They call a library, fit a model, get a prediction, and move on. And that's not a bad thing. But it does turn the model into a black box. When something goes wrong, you don't know why. When results look suspicious, you don't know what to check. If you're new to machine learning, this video will build everything from the ground up. And if you already use linear regression at work, but don't really know what's happening under the hood, this video is for you too. No assumptions, no skipped steps. By the end of this video, linear regression will not feel like a black box anymore. You'll know exactly what the model is doing, how it learns, and how to tell if it's actually working or quietly failing. Here's how we'll do it. We'll start with the problem linear regression is trying to solve. Then we'll build the equation from scratch. You'll see how predictions are made, how error is measured, and how the model learns step by step using gradient descent. Then we'll go deeper. You'll understand regularization, L1, L2, and Elasticnet. Why feature scaling matters, how overfitting actually happens, and how models are evaluated using real metrics like MSE, R-squared, and p-values. And finally, we'll connect all of this to real machine learning code. You'll see how libraries implement everything you just learned. So when you use a model, you actually know what it's doing. This is not a shortcut video, it's a clarity video. If you want to really understand linear regression, I highly recommend that you start from the beginning. However, you can use the video markers in the description to jump between the topics. Let's start. Imagine you're trying to predict house prices based on size. You look at some past data and think, bigger houses cost more. So you draw a line through the points. But here's the problem. Someone else draws a different line, and someone else draws another. All of them look reasonable. So which one is correct? This is exactly what we do when we rely on intuition. Our brains are great at patterns, but terrible at consistency. Now imagine this isn't house prices, it's medical risk, or stock prices, or loan approvals. A small change in judgment can mean a huge real-world impact. Machine learning libraries solve this with one line of code. But if you don't know what's happening inside, you don't know why a model made a prediction. You can't debug it, you can't trust it, and you definitely can't improve it. So what we really need is three things. A clear rule for drawing the line, a way to measure how good the line is, a method to find the best possible line, not just a good-looking one. And this is exactly where linear regression comes in. To understand linear regression properly, we're going to work with a very small data set. Not thousands of points, not fancy data, just enough to see every step clearly. Here, X represents house size and Y represents house price. These numbers are small on purpose, so we can actually calculate everything by hand. Let's plot these points. Each dot represents one house. Already we can see a trend. As size increases, price generally increases. Our goal is to describe this relationship using a straight line. Not because the world is perfectly linear, but because a straight line is the simplest model we can start with. But here's the key question. Which line should we choose? And more importantly, how do we choose it mathematically, not by intuition? To answer that, we first need to define what a line actually is in math. That's where we go next. Now that we have the data points, we need a rule that takes a house size and gives us a predicted price. Linear regression starts with the simplest possible rule, a straight line. This is the entire model. For any input x, the line outputs a prediction y hat, meaning predicted y. Let's break this into two parts. First, b is the intercept. It's the value of y hat when x equals 0. So b decides where the line starts on the y-axis. If I increase b, the whole line moves up. If I decrease b, the whole line moves down. Now the slope, m. This decides how steep the line is. If m is large, the line rises quickly. Price increases a lot when size increases. If m is small, the line rises slowly. So m controls the tilt and b controls the vertical shift. And here's the big idea. Every choice of m and b gives a different line and a different set of predictions. Now that we understand the equation y equals mx plus b, the real question is, how do we actually find m and b? There are two main ways to do it. One is called the method of least squares. The other is called gradient descent. In this scene, we'll solve it directly using least squares. No iterations, no learning rate, just pure algebra. We already know that for each data point, there is some error. That error is the difference between the actual value and our predicted value. If we square that error and add it up for all points, we get the total squared error. Least squares means choose m and b so that this total squared error is as small as possible. If we take derivatives of this expression with respect to m and b and set them equal to 0, we can solve for m and b directly. These formulas give us the exact line that minimizes squared error. This is the normal equation, written in simple form. Let's calculate everything step by step. First, compute sums. Now plug into slope formula. Compute numerator, denominator. Now calculate b. So our final equation is, and this line minimizes the total squared error. Notice something important. We didn't guess. We didn't iterate. We didn't move step by step. We jumped directly to the exact minimum. That's the power of the normal equation. So if we can solve linear regression like this, why do we need gradient descent? Because this method works beautifully for simple linear regression. But when data sets get very large or when models become more complex, solving everything algebraically becomes difficult. So instead of jumping directly to the answer, we learn how to walk downhill toward it. And that's where gradient descent comes in. Let's pause for a second and zoom out. This simple equation gives us two powerful controls. One control lets us move the line up and down. The other control lets us tilt the line left or right. That's it. That's the core idea. With just these two adjustments, we can draw any straight line we want. Now, when we place this line on top of our data points, the line starts making predictions. For a given house size, the line tells us what price it thinks makes sense. But drawing a line is not enough. Some lines will be close to the dots, some lines will be far away. So the next question is obvious. How do we know if a line is good or bad? To answer that, we need two things. First, a way to measure how far the line is from the data points. And second, a way to compare different lines and decide which one is better. That's where the real math begins. Next, we learn how to measure error. one point at a time. And once we can measure error, we can finally teach the model how to improve. This is essential for all of you aspiring data scientists. It is important to understand how to check for errors in the data and to persistently enhance accuracy of the line until the desired objective is achieved. To answer that, we need a way to measure how wrong a line is, point by point. That's next. Now that we can draw a line, let's answer the most important question so far. How wrong is this line? Because a line that looks okay can still make bad predictions. For any house size, the line gives us a predicted price. This value comes directly from the equation. This is what the model thinks the price should be. But we already know the actual price from the data. The difference between the actual price and the predicted price is called the error. You can think of it as the vertical distance between the dot and the line. If the line predicts too high, the error is negative. If the line predicts too low, the error is positive. Either way, the error tells us how wrong the model is for that point. But a model doesn't make just one prediction. It makes predictions for every data point. So we don't just have one error, we have many. Some small, some big. Here's the problem. One line might be very wrong for one point, but good for the others. Another line might be a little wrong everywhere. Which one is better? We can't answer that by looking. What we need is a single number that tells us how bad a line is overall. A number we can compare across different lines. Lower number means better line. And that's exactly what we'll do next. We'll combine all these errors into one value, the loss. That's where learning really begins. So now we have a bunch of errors, one for each data point. But we still don't have a single way to judge how good or bad the line is. We need one score. You might think we can just add all the errors together. But there's a problem. Positive errors and negative errors cancel each other out. A very bad line could end up looking perfect. So instead, we square the errors. Squaring does two important things. First, it makes all errors positive. Second, it punishes large mistakes more than small ones. For each point, we take the actual value, subtract the predicted value, and then square the result. Now every mistake counts. Finally, we take the average of all these squared errors. This gives us mean squared error. One number, one judgment. Lower MSE means the line fits the data better. Higher MSE means the line makes worse predictions. Now we can compare lines objectively. This is the score the model cares about. It doesn't know about dots or graphs. It only knows one thing: reduce this number. So now we have a way to measure how bad a line is. The final question is, how do we change the line to make this number smaller? In the previous scene, we calculated something called mean squared error. This number tells us how bad a line is. Smaller number means better predictions. Now here's the big idea. Every straight line we can draw has its own MSE. When we change M, the line tilts. When we change B, the line moves up or down. So by changing M and B, we can draw every possible straight line. Our job is to find the one line that gives the lowest MSE. The best line does not mean it passes through all points. It means, on average, it makes the smallest mistakes. That's what MSE measures. In theory, We could try every possible line. Change M, calculate MSE. Change B, calculate MSE. Repeat forever. But there are infinitely many lines. So we need a smarter way. Instead of jumping randomly, we improve the line step by step. We start with a guess. Then we slightly adjust the line. If MSE goes down, good. If MSE goes up, bad. This is what learning means in machine learning. Not magic, not guessing, just repeatedly changing M and B to reduce MSE. The only question left is, how do we know which direction to change M and B? That's where gradients come in. So we need direction, not just movement. Gradient means which way makes MSE go down fastest. Gradients tell us how to change M and B. This is how learning becomes systematic, not trial and error. In the last scene, we said our goal is simple. Change M and B so that MSE becomes smaller. But there's a problem. When we move the line, there are many directions we could move it. We could try guessing, change the line a little, recalculate MSE. If it gets worse, undo it. But that would be slow and unreliable. We need a rule. Think about standing on a hill. If you take one step in different directions, some steps go down and some go up. What we want is the direction that goes down the fastest. The gradient is just a direction. It tells us which way MSE increases the fastest. So if we go in the opposite direction, MSE decreases the fastest. Remember, our line is controlled by M and B. So the gradient tells us two things. How should we change M and how should we change B? Mathematically, we calculate two gradients. One tells us how MSE changes when M changes. The other tells us how MSE changes when B changes. You don't need to memorize these formulas. Now the process becomes very clear. Calculate the gradients, move M and B slightly in the opposite direction, recalculate MSE, repeat. This is why machine learning scales. The same idea works with 2 parameters or 2 million. Gradients tell the model exactly how to improve. In the next scene, we'll actually calculate one gradient step with real numbers and see the math behind it, so you can see learning happen on paper. We will pick actual values of M and B, calculate gradients, update them, watch MSE drop. We always start with a guess. It doesn't have to be good. It just has to be a starting point. Let's say M is equal to 0 and B is equal to 0. Plot the data points. Draw the prediction line. Use this line to make predictions. For each x value, we plug it into the equation. Whatever comes out is the predicted value. Now we compare prediction with reality. Error is just actual minus predicted. Now we square the errors, add them up, and take the average. That gives us MSE. Now comes the gradient. This tells us how to change M and B. We'll calculate two numbers. Now we update the line. We move in the opposite direction of the gradient, using a small step size. This gives us a new line. Same data, better position. Now we do the same thing again. Make predictions, calculate errors, calculate MSE. Nothing magical happened. We didn't guess. We followed the math, and the line got better. This is one step of gradient descent. Training just means repeating this again and again. If you want to get your hands dirty with the math we just covered, I've made the entire gradient descent script available for you. You can find the source code on my GitHub, or if you want to run it right now without installing anything, just click the Google Colab link. It's pre-configured with the data table we use today, so you can hit play and watch the MSE drop in real time. Up until now, we've been predicting house prices using just one input, house size. That was intentional. Using a single feature helped us understand how linear regression works step by step. But let's be honest for a moment. If someone told you they could predict house prices using only size, you probably wouldn't trust that model. Because real life is messier than that. In reality, many things affect the price of a house. The number of bedrooms, the location, how old the house is, how far it is from the city. In machine learning, we give these inputs a name. We call them features. A feature is not a fancy concept. It's just a measurable piece of information we use to make a prediction. When we had just one feature, our model was a straight line. One input, one output. Easy to draw. But now we have more than one input, and when inputs increase, the shape of the model changes. Instead of fitting a line, we are fitting a surface. The equation also grows, but in a very predictable way. Each feature gets its own weight, and we still add everything together. So instead of one slope, we now have many. Each weight tells us how strongly a feature influences the prediction. If a weight is large, that feature matters a lot. If a weight is small, that feature matters less. So the model isn't just fitting data, it's learning what to care about. Now here's the most important part. Even though this looks more complex, the learning process has not changed. We still make predictions, we still measure error, we still calculate MSE, and we still use gradients to improve the model. The only real difference is this. Instead of adjusting one slope, we adjust many weights, one for each feature. But mathematically, it's the same idea repeated. So linear regression didn't stop being linear. It just gained more dimensions. And that idea, learning weights using gradients, scales all the way up to neural networks. Next, we'll look at how this is written cleanly using vectors, without fear. Until now, we predicted price using only house size. That gave us one line. But in real life, size alone isn't enough. So now we are going to add one more feature, number of bedrooms. And we'll do the exact same training process, but with one extra weight. The equation grows in a simple way. Each feature gets its own weight. So now predicted price becomes weight for size times size plus weight for bedrooms times bedrooms plus a bias. Just like before, training starts with a guess. Let's start simple. M1 equals 0, M2 equals 0, B equals 0. That means the model predicts 0 for everyone. It's a bad model, but it's a starting point. Now we compute error, actual minus predicted. Since every prediction is 0, the error is just the actual value. Then we square errors, average them, and we get MSE, one number that judges the model. Now the model needs direction, so we calculate gradients, one for each parameter. Think of it like this. One gradient tells us how to change the weight for size. One tells us how to change the weight for bedrooms. And one tells us how to change the bias. Now we update parameters by moving opposite to the gradient. We'll use a small learning rate so we don't overshoot. Let's choose alpha equals 0.01. Now we build a new prediction using the updated weights. Same data, new model. When predictions change, errors change. And when errors change, MSE changes. So let's calculate MSE again. So nothing magical happened. We added a feature that added one more weight, and the exact same training loop worked again. This is why machine learning scales. The process stays the same, only the number of weights grows. In the last scene, we added a second feature and did one gradient descent step. We started with a tellable model, and after one update, the MSE dropped a lot. Now we are going to do the exact same process one more time. Same dataset, same formula, same learning rate. Just one more step, and we'll see if MSE drops further. First, we make predictions using our current weights. We take each row, plug x1 and x2 into the equation, and that gives us y hat. Because we updated the weights, predictions will be different than last time. Next, we calculate error for each row. Error is actual minus predicted. These errors are what gradients use to decide the direction of improvement. So we'll compute errors, and then we'll summarize them using sums. Now we compute the gradients. Same formulas as before. We take those sums and multiply by minus 2 over n. This gives us one gradient for m1, one for m2, and one for b. Now we update parameters by moving opposite to the gradient. Same learning rate, alpha equals 0.01. This gives us our second update. Now we repeat the same thing one last time. Make new predictions, compute errors, and calculate the new MSE. This is the moment of truth. Did the second step improve the model again? So we didn't do anything new. We simply repeated the same loop. But look at what happened. The MSE dropped again. This is training. Not one magical calculation, just repeated small improvements. If we keep going, the model keeps adjusting until it can't reduce the loss much anymore. If you want to get your hands dirty with the math we just covered, I've made the entire gradient descent script available for you. You can find the source code on my GitHub, or if you want to run it right now without installing anything, just click the Google Colab link. It's pre-configured with the data table we use today, so you can hit play and watch the MSE drop in real time. So far, every time we added something, more steps, more features, the model got better. So it's natural to think, why not just keep adding more features? More information should mean better predictions. But this is where real machine learning gets tricky. Let's start with a subtle but very common problem: feature scaling. Imagine we are predicting house prices using two features: house size measured in square meters and distance to the city measured in kilometers. House size might range from 50 to 300. Distance might range from 1 to 10. These numbers live on completely different scales. Now remember how gradient descent works. It looks at how much the loss changes when we adjust each weight. If one feature has much larger numbers, its gradient becomes much larger. So the model starts focusing more on that feature, not because it's more important, but simply because the numbers are bigger. That's not learning. That's imbalance. Feature scaling fixes this by putting all features on a similar scale. Not by changing their meaning, but by changing their units. So gradients behave fairly, and learning becomes smoother and faster. Now let's talk about a different problem. Sometimes adding more features makes training errors smaller, but predictions worse. This problem is called overfitting. The model starts memorizing the data instead of learning patterns. Every new feature adds flexibility, more weights, more ways to bend the model. At some point, the model stops learning the signal and starts learning the noise. Training error goes down. Real-world performance goes down. Feature scaling and overfitting are different problems, but they teach the same lesson. More features don't automatically mean better models. Good machine learning is about balance, not just math. In the next scene, we'll see how machine learning deals with these problems, how we control complexity, and how we decide which features actually matter. In the previous scene, we saw two problems that show up in real machine learning: feature scaling and overfitting. In this scene, we'll focus on the first one, not conceptually, but mathematically. Feature scaling does not change the meaning of your data. It does not add information, and it does not remove information. It only changes the units your model sees, so that all features live on a comparable scale. The most common way to scale features is called standardization. The idea is simple. We take a feature, subtract its average, and divide by its spread. This transforms the feature so that it's centered around 0. Here's the formula. Don't panic, we'll walk through it slowly. Let's do this once completely by hand. Suppose we have a feature, house size. Values are 1, 2, 3, 4, 5, 6, 7. First, we compute the mean. Next, we compute the standard deviation. This measures how spread out the data is. Now we scale one value, say x equals 6. After standardization, features are centered around 0. Most values fall between -2 and +2. No feature dominates just because its numbers are large. Now here's why this matters for learning. Gradients depend on the size of feature values. When features are scaled, all gradients behave more evenly, and gradient descent moves smoothly toward the minimum. One important rule before we move on. You must compute the mean and standard deviation using only training data. Then apply the same scaling to validation and test data. Otherwise, you leak information. So feature scaling is not optional. It's a requirement for stable learning. Now let's talk about overfitting. Overfitting happens when the model becomes too flexible. Mathematically, that means too many parameters. Every feature adds a weight. Every weight adds a degree of freedom. Here's the key mathematical symptom of overfitting. Training error keeps decreasing, but validation error starts increasing. The model is minimizing loss, but on the wrong data. Gradient descent doesn't know about overfitting. It only knows how to reduce training loss. If the model has enough parameters, it will happily fit noise. The math is doing exactly what we asked. The problem is what we asked it to do. But how do we measure training error? How do we measure validation error? How do we know overfitting is happening? So far, we have talked about error as if it's just one number. We calculated MSE and tried to make it smaller. But in real machine learning, one error number is not enough. We must ask a deeper question. Is the model learning a pattern or memorizing data? To answer that question, we split the data. One part is used to train the model, the other part is kept hidden. This hidden data is called validation data. The model never learns from it. It only gets tested on it. First, we train the model using only the training data. We make predictions, we compute errors, and we calculate training MSE. Now comes the key difference. We freeze the model. No learning, no updates. We use the same weights and bias and we calculate error on the validation data. Now we repeat training. Each time, training error usually goes down. That's expected. The model is getting better at fitting the training data. But after a point, something interesting happens. Training error keeps decreasing. Validation error stops improving and then starts increasing. This tells us something very specific. The model is learning patterns that only exist in the training data. It is no longer generalizing. It is memorizing noise. Mathematically, this happens because the model has too much freedom. Now let's connect this back to feature scaling. Scaling does not prevent overfitting. But without scaling, gradients behave unevenly. That makes learning unstable and unpredictable. So scaling is about stability. Overfitting is about excess freedom. Let's summarize this mathematically. Training error answers one question. How well does the model fit the data it learned from? Validation error answers a different question. How well does the model generalize? If both go down, learning is good. If training goes down and validation goes up, overfitting. Now we have a dilemma. Gradient descent always tries to reduce training error, but reducing training error alone can hurt generalization. So we need a way to control the model mathematically, to reward simplicity and punish excessive complexity. That penalty is called regularization, and that's where we go next. In the last scene, we saw a problem we couldn't ignore. Training error kept going down, but validation error started going up. The model was doing exactly what we asked, but what we asked was incomplete. So instead of changing the optimizer, we change the objective. Regularization means adding a rule that says fit the data, but don't make the model too complex. Mathematically, we do this by penalizing large weights. Big weights mean aggressive fitting. Small weights mean smoother behavior. Let's anchor ourselves in the math. So far, our loss function was mean squared error. L2 regularization modifies this loss. We add a penalty for large weights. This penalty is proportional to the square of each weight. The model now balances two goals: fit the data and keep weights small. Lambda controls how strict the rule is. If lambda is 0, we are back to normal training. If lambda is large, the model strongly avoids large weights. So lambda controls the trade-off between fitting and simplicity. Now here's the most important part. Regularization doesn't fight gradient descent. It changes the gradients. Each weight update now has two forces. One force reduces error, the other pulls weights back towards 0. Mathematically, this adds a simple term to the gradient. Each weight gets an extra push towards 0. By keeping weights small, the model can't twist itself to fit noise. It's forced to learn broader patterns. That's why validation error improves. L2 regularization doesn't magically fix bad data. It doesn't choose features for you, and it doesn't replace validation. It simply adds discipline to learning. So now we've learned how to control models mathematically. Next, we'll see a different kind of regularization, one that can actually turn features off. In the last scene, we learned about L2 regularization. L2 helps control overfitting by keeping weights small. It smooths the model and prevents extreme behavior. But L2 has a limitation. It never truly removes a feature. Every feature still contributes, just a little. Now imagine this situation. You give the model 10 features, but only 3 of them actually matter. Ideally, the model should ignore the useless ones. L1 regularization allows exactly that. This idea is called sparsity. Let's compare L2 and L1 directly. L2 pushes weights towards 0. L1 pushes weights to 0. That single difference changes how the model behaves. L2 shrinks, L1 deletes. Now let's look at the math. The prediction error stays the same. Only the penalty term changes. Let's take a look at the equation. Instead of squaring the weights, we take their absolute values. This absolute value is the key. Unlike squaring, it creates a sharp corner at 0. Gradient descent behaves differently near sharp corners. Once a weight gets close to 0, L1 tends to push it exactly to 0. 0 becomes a stable solution. During training, something interesting happens. Some weights keep updating, others shrink, and then stop moving entirely. When a weight reaches 0, that feature no longer affects predictions. This is why L1 is often used for feature selection. You don't manually choose which features matter. You let the math decide. Useless features disappear. Useful features remain. L1 doesn't guess importance. It proves it. L1 works best when you have many features, only a few are important, and interpretability matters. But L1 has limitations. When features are strongly correlated, L1 may behave unpredictably. Here's the clean takeaway. L2 says all features can stay but behave. L1 says only the useful ones survive. In practice, we often combine both ideas: control complexity and select features. That leads to Elasticnet. We have learned two powerful tools. L2 regularization shrinks weights to control overfitting. L1 regularization can push some weights exactly to 0, so it can remove features. So now the natural question is, can we get the benefits of both? Yes, and that combination is called Elasticnet. Elasticnet adds two penalties to the loss function. One penalty encourages small weights, that's L2. The other encourages zero weights, that's L1. So the model stays stable and can drop useless features. Let's look at the math slowly. We still start with our prediction error, MSE. Now we add the L1 penalty and the L2 penalty. So the loss becomes error plus two kinds of discipline. Elasticnet exists because real-world data is messy. In real datasets, features are often correlated. Example, house size and number of bedrooms. L1 alone can behave unpredictably when two features are similar. It might keep one and kill the other randomly. L2 alone keeps everything, even useless features. Elasticnet balances both. Here's what Elasticnet does to weights during training. L2 gently pulls all weights towards zero. L1 tries to snap some weights exactly to zero. Elasticnet does both at the same time. So you usually end up with some weights are exactly zero, and the remaining ones are not too large. Elasticnet has two knobs. Lambda 1 controls sparsity. Higher lambda 1 means more zeros. Lambda 2 controls shrinkage. Higher lambda 2 means smaller weights overall. So tuning Elasticnet is really about deciding, do I want more feature selection or more stability? Now the key question is, how do we choose these lambdas? We don't guess, we measure. We try different values and check validation error. The best setting is the one that performs best on validation data. So here's the final takeaway. L2 prevents weights from exploding. L1 can remove unnecessary features. Elasticnet combines both. That's why it's popular in real-world machine learning, especially when features are many and correlated. At this point, you understand the full toolkit for linear models. Next, how to implement everything cleanly using vector notation. Up to now, we've done everything step by step. We wrote equations for predictions, we computed errors, we calculated gradients, and we updated weights. That's perfect for understanding. But it's not how real machine learning systems work. So far, we've been thinking one data point at a time, one row, one prediction, one error. But imagine having 1,000,000 data points and 100 features. Writing loops for that would be slow, very slow. Vector form solves this by grouping everything together. Instead of working with single numbers, we work with vectors and matrices. We don't change the model, we don't change the math, we only change how it's written. Let's define the three objects used in vector form. X is the feature matrix. Each row is one data point. Each column is one feature. Theta is the weight vector. One weight per feature. Y is the output vector. One value per data point. Here's the big moment. All predictions for all data points can be written as one line. This single equation replaces hundreds of loops. Now let's look at loss. Earlier, we wrote mean squared error as a sum. In vector form, it becomes a dot product. Here's why vector form is so powerful. Gradient descent becomes one clean update. No loops, no manual summation. This is exactly how machine learning libraries work. They store data as matrices. They use optimized linear algebra, and they rely on vectorized operations. When you call fit, this is the math happening underneath. Vectorized code is fast for three reasons. 1. Fewer Python loops. 2. Optimized low-level math. 3. Easy parallelization on CPUs and GPUs. That's why ML scales. So remember this. Vector form does not change what the model learns. It changes how efficiently we compute it. Vector form is the language of machine learning systems. At this point, you understand linear models end to end. Next, implementation. Writing this in code. Up to now, we learned the math. Now we'll build it from scratch in NumPy. No scikit-learn yet. We'll implement the learning loop ourselves. We'll also do the real-world stuff: train, validation, test, and regularization. We'll use the same dataset from the video: 7 houses, 2 features, size and bedrooms, target, price. To detect overfitting, we must evaluate on unseen data. Training data updates the model. Validation data helps us choose hyperparameters like lambda. Test data is the final exam. Scaling must be learned only from training data. We compute mean and standard deviation on training set. Then apply the same transformation to validation and test. Now the real learning loop. We predict y hat equals x theta plus b. Compute errors and MSE. Compute gradients. Update weights. Repeat. Now we add discipline. L2 adds a penalty for large weights. So the model fits data but avoids extreme weights that overfit. Once we pick lambda using validation, we do one final evaluation on the test set. That's our honest performance estimate. So far, we've understood linear regression step by step with math and visuals. Now we are going to build the full thing in Python using NumPy, the way libraries actually do it. And we'll do it properly, like real machine learning, with training, validation, testing, scaling, and regularization. No black box, everything visible. First, here's our raw dataset, the same one we used across the video. 2 features: house size and number of bedrooms. And the target is price. Notice how small this dataset is. We're using it for learning and clarity, not to win accuracy. The goal is to see the mechanics. Now we split the data into 3 parts. Training data is the only part that updates weights. Validation data is never used for learning. It's used to check if we are generalizing. And test data is the final exam. This split is how we detect overfitting in real machine learning. This validation row is the one the model is not allowed to learn from. It can only be tested on it. Now we do feature scaling, specifically standardization. And this is super important. We compute the mean and standard deviation using only the training data. That prevents data leakage, meaning we don't accidentally learn from the validation or test set. So here are the training means and training standard deviations for each feature. These 2 numbers, mean and standard deviation, are the scaling rules we'll reuse everywhere. Now we apply scaling to training, validation, and test. The raw numbers become scale numbers centered around 0. Same information, just a fair scale, so gradient descent behaves properly. This step doesn't make the model smarter. It makes learning smoother and stable. Now we build prediction. This is the exact equation we've been using all along. We take our feature matrix X, multiply it by weights W, and add bias B. That gives us predicted values, y hat. And the key point is, these predictions are just numbers. No magic, just multiplication and addition. Here are the predictions for the training set at this moment. You can literally see the values the model believes. Now we train using gradient descent. Every epoch, the model makes predictions, computes errors, computes MSE, calculates gradients, and updates weights. And we track two errors. Training MSE, error on the data it learned from. Validation MSE, error on unseen data. This graph is one of the most important graphs in machine learning. If training error goes down, that means the model is fitting training data. But validation error tells us if those patterns actually generalize. If validation stops improving or starts rising, that's the warning sign, overfitting. Now we add regularization. Specifically, L2 regularization. This changes the loss function. Instead of only minimizing error, we also penalize large weights. So the model is pushed to stay simpler. And now look at the difference. Without regularization, the model can become too aggressive. With L2, the weights are controlled, so the model tends to generalize better. Regularization is basically discipline. It says, fit the data, but don't overreact. Now, how do we choose lambda? We don't guess. We use validation. We try different lambda values and choose the one with the lowest validation MSE. That's how real machine learning is done. You measure, not assume. Once we choose our best settings using validation, we do one final evaluation on the test set. The test set is untouched during training. So this is the honest performance. Here's the true price. Here's the predicted price. And here's the error. This is the moment you stop trusting training error and start trusting real evaluation. So now you've seen the full machine learning workflow from scratch. Raw data, split into train, validation, and test. Scale properly. Train using gradient descent. Watch loss curves. Control complexity with regularization. And finally, test on unseen data. Nothing here is a black box. It's math plus feedback plus discipline. If you want to get your hands dirty with the math we just covered, I've made the entire gradient descent script available for you. You can find the source code on my GitHub, or if you want to run it right now without installing anything, just click the Google Colab link. It's pre-configured with the data table we use today, so you can hit play and watch the MSE drop in real time. Up to now, we did linear regression the honest way. We calculated everything ourselves. That's how you stop treating machine learning like a black box. Now we are going to do the same thing using real machine learning models. There are different linear regression models, and each one fixes a different real-world problem. Overfitting, too many features, noisy data, outliers. In this video, I'll show you what models exist, what they do, and how to choose the right one. Bayes linear regression, also called ordinary least squares, finds coefficients that minimize squared error. It works great when relationship is roughly linear, noise is normalish, features aren't too correlated. But it struggles with multi-collinearity, overfitting, and outliers. Ridge adds an L2 penalty. It shrinks coefficients but typically doesn't eliminate features. Use ridge when you have many features. Features are correlated. You want stability and better generalization. Ridge equals shrink, don't delete. Lasso uses an L1 penalty, and this is special. It can push some coefficients to exactly 0. That means Lasso performs automatic feature selection. Lasso equals shrink plus delete irrelevant. Elasticnet combines ridge and lasso. It's great when you have many features, many are correlated. You still want feature selection but not too harsh. Elasticnet equals best of both worlds. If your data has outliers, OLS can get dragged. Huber regression uses a loss that behaves like squared loss for small errors, but becomes more linear for large errors. Translation: it reduces outlier influence. Huber equals robust to outliers. Here's our raw data set, same one from the video. 2 features, house size and number of bedrooms. Target, the house price. It's a small data set, which is perfect for learning because you can see every row. In real projects, you'd have thousands of rows, but the workflow is exactly the same. Next, we do something that separates real machine learning from guessing. We split the data into training, validation, and test. Training data is the only data the model is allowed to learn from. Validation data is used to choose settings like regularization strength. And test data is the final exam, untouched until the very end. This is how we catch overfitting. Now we build the models using a pipeline. The pipeline ensures scaling is done correctly. It learns mean and standard deviation only from training data, and then applies that same transformation to validation and test. This prevents data leakage, which is one of the most common beginner mistakes. Now we train multiple regression models. Linear regression is the basic model, no regularization. Ridge is L2 regularization. It shrinks weights. Lasso is L1 regularization. It can push some weights to 0. Elasticnet combines both. Now look at this results table. For each model we are showing, train MSE, error on training data. Validation MSE, error on unseen validation data. Test MSE, error on the final exam. R squared, how much variation the model explains. Adjusted R squared, a more honest R squared that penalizes extra features. And the final test prediction value. This is exactly how we evaluate models in practice, not just one metric. Quick intuition. MSE tells us how wrong are our predictions on average. Lower is better. R squared tells us How much of the variation in price does the model explain? Higher is better. And adjusted R squared is like R squared with a penalty. It helps prevent us from being impressed by unnecessary complexity. So we look at MSE for accuracy and R squared for explanatory power. Now here's something important. Most library models like linear regression solve the problem in one shot, so you don't see the learning process. But earlier in the video, we learned gradient descent and epochs. So to visualize that learning, we use SGD regressor. This model learns iteratively, just like our manual gradient descent. This plot is the heartbeat of machine learning. Training MSE usually goes down because the optimizer is trying to fit training data. Validation MSE tells us whether this learning generalizes. And this vertical line marks the best epoch, where validation error is lowest. That's where we should stop training if we want the best generalization. Now we compute the same metrics for SGD regressor. Train MSE, validation MSE, test MSE, and R squared. So we can compare iterative learning to the closed form models. The goal here is not to say SGD is better. The goal is to show that library training follows the exact loop we learned. Now we look at something from statistics, p-values. This helps answer which features are actually important. Stats models gives us a full regression summary, coefficients, standard errors, and p-values. One caution, p-values become meaningful with larger data sets. With only a few data points, they can be unstable. So we are using them here to understand the concept, not to make scientific claims. If you want to get your hands dirty with the math we just covered, I've made the entire gradient descent script available for you. You can find the source code on my GitHub, or if you want to run it right now without installing anything, just click the Google Colab link. It's pre-configured with the data table we use today, so you can hit play and watch the MSE drop in real time. So far, we have trained models and made predictions. But machine learning doesn't end with training. The real question is, how do we know if a model is actually good? That's where evaluation metrics come in. Let's start with R squared, also called R squared. R squared answers one simple question. How much of the variation in the output does my model explain? Imagine house prices vary because of many factors. If my model explains most of that variation, R squared will be close to 1. If it explains almost nothing, R squared will be close to 0. And if it performs worse than predicting the average price, R squared can even be negative. Under the hood, R squared compares two things: how wrong our model is versus how wrong we'd be if we always predicted the average. Here's the trap. R squared almost always increases when you add more features, even if those features are useless. So a high R squared doesn't automatically mean a good model. This is why we use adjusted R squared. Adjusted R squared adds a penalty for unnecessary features. If a new feature doesn't truly help, adjusted R squared will go down. Now let's talk about p-values. P-values answer a different question. If this feature had no real effect, how surprising would this coefficient be? A small p-value means the feature is likely meaningful. A large p-value means the effect could just be noise. By convention, p less than 0.05 implies statistically significant. P greater than or equal to 0.05 implies weak evidence. This part is very important. P-values only make sense with enough data. With very small datasets, p-values can be unstable. So in real machine learning, we use p-values as one signal, not the final judge. Here's the clean mental model. MSE tells you how wrong your predictions are. R squared tells you how much variation you explain. Adjusted R-squared tells you whether extra features are worth it. P-values tell you which features are likely meaningful. No single metric tells the whole story. Good models balance all of them. When most people learn machine learning, they start with models. But we did the opposite. We started with the data, the math, and the learning process. You saw how a straight line is not magic. It's just parameters moving step by step to reduce error. At this point, linear regression should no longer feel like a black box. You know exactly what the model is doing. You know how it learns. And you know how to tell if it's lying to you. That's the real skill in machine learning. So far in this notebook, we've been using scikit-learn, linear regression, ridge, lasso, Elasticnet. And there's something important to understand. Scikit-learn runs on the CPU. Even if you enable GPU in Google Colab, these models still execute on the CPU. That's not a limitation. That's just how scikit-learn is designed. For small to medium datasets, CPU is perfectly fine. Linear regression is computationally lightweight. But as models get larger, as datasets grow into millions of rows, or when we move into deep learning, GPU becomes very important. Neural networks, large embeddings, huge matrix multiplications. That's where GPU acceleration makes a big difference. So now, just to demonstrate the difference, we'll move from scikit-learn to PyTorch. PyTorch is a GPU-enabled deep learning library. It allows us to move tensors directly onto the GPU. The math is exactly the same, only the hardware changes. Quick demo time. So I'll show you the same learning idea running on GPU using PyTorch. First, I'm checking if a GPU is available in Colab. CUDA available, yes. And here's the GPU name. This confirms Colab can run computations on GPU. Important note, even if the GPU is enabled, scikit-learn models still run on CPU. So linear regression, ridge, lasso, Elasticnet in sklearn, CPU only. To actually use GPU, we switch to a GPU native library like PyTorch. Now here's the key step. In PyTorch, we choose a device. CUDA means GPU. Then we create tensors on that device. This means our data is physically moved into GPU memory. Next, we do standardization, just like before. But notice, we calculate mean and standard deviation using training data only. Then we apply that same transformation to validation and test. This is crucial. It prevents data leakage. Same rule even on GPU. Now we train. This loop is the exact same learning loop you learned earlier. We predict using y-hat. We compute MSE. We optionally add regularization. Then we compute gradients and update weights. In PyTorch, loss.backward calculates gradients automatically. And then we update the weights. Now I trained 4 variants. Plain linear regression, L2 ridge style, L1 lasso style, and Elasticnet, a mix of both. Same concept, just different penalty terms. Now we plot validation MSE over epochs. This is why this demo is so valuable. Closed form solvers hide training dynamics. But here, we can literally see learning happening epoch by epoch. And we can compare how regularization changes the behavior. Training is not just a result, it's a process. One important clarification. Linear regression often runs perfectly fine on CPU, even with lots of rows. GPU isn't about better accuracy. GPU is about speeding up heavy computation at scale, especially for deep learning. So the key takeaway is simple. The math didn't change. We still have predictions, loss, gradients, and updates. What changed is the engine, CPU versus GPU. And now that you understand this, you're ready to understand how neural networks train, because it's the same loop. If you want to get your hands dirty with the math we just covered, I've made the entire gradient descent script available for you. You can find the source code on my GitHub, or if you want to run it right now without installing anything, just click the Google Colab link. It's pre-configured with the data table we use today, so you can hit play and watch the MSE drop in real time. Let's take a step back and recap what we have learned. This started with a simple equation. Y equals mx plus b. And look where we ended up. Here's everything we've learned in this video. 1. The foundation. We understood what a straight line really means. Slope controls tilt. Intercept controls vertical shift. 2. Prediction and error. We learned how predictions are calculated. We measured error. We squared it, and we built the mean squared error loss. 3. 2 ways to solve linear regression. We solved it using the method of least squares, direct algebra, closed form solution, and we also solved it using gradient descent, step-by-step optimization. 4. Why optimization matters. We saw why gradient descent becomes necessary when data grows, when models get more complex, when closed-form solutions no longer exist. 5. Regularization. We understood L2, ridge, which shrinks weights. We understood L1, lasso, which can eliminate features, and Elasticnet, which combines both. We saw how regularization controls overfitting. 6. Feature scaling and overfitting. We learned why scaling matters, how training error and validation error behave, and how overfitting actually shows up in practice. 7. Model evaluation. We used MSE. We used R-squared. We discussed adjusted R-squared. We looked at p-values. We didn't just train a model, we evaluated it properly. 8. From math to code. We implemented everything in NumPy. Then we used scikit-learn. Then we moved to PyTorch and even ran models on the GPU. Linear regression is not just a formula, it is a complete learning system. Data, prediction, loss, optimization, evaluation. And now you understand every part of it. At the beginning of this video, linear regression might have felt like a black box. Now it shouldn't. You know what's happening under the hood. You know how the parameters move. You know how to detect overfitting. You know how to evaluate performance. That's not memorization. That's understanding. But linear regression has a hard limit. It predicts numbers. What if the answer is not a number, but a decision? Yes or no? Spam or not spam? Buy or don't buy? In the next video, we take everything you've learned, loss, gradient descent, regularization, vector form, and we change just one thing: the output. Logistic regression is not a new model. It's linear regression with a smarter question. And once you understand that, classification will never feel like magic again.